So yeah, welcome everybody to what is the sixth session from Engineering New Zealand's Lessons to be Learned series. And of course, this session's been hosted by the New Zealand Hydropower Group, of which I'm the chair. For those that don't know, the New Zealand Hydropower Group's new group, technical interest group under Engineering New Zealand, looking at technical interests of hydropower engineers here in New Zealand. Obviously, we've done a number of seminars, and in September we'll be hosting our inaugural conference down here in Christchurch. So yeah, if this tickles your interest and you want to know more about hydro, then please Google us or reach out. So as we all know, this session's around lessons to be learned on a disaster at a Russian power station over 10 years ago. Tragically resulted in the death of a number of people, but there was certainly some good lessons to be learned on that. And our speaker is going to tell us all about that. So very pleased to have Mr. Don Erpenbeck on today. So Don's a Vice President at Stantec, and he serves as Stantec's Global Sector Lead for the dams and hydropower business. So he's a licensed mechanical engineer in Illinois, and is a technical expert in large rotating machinery with over 30 years experience working on some of the largest hydro units in the world. In this presentation, Don will discuss the sequence of events, potential root causes, lessons learned, and unforeseen impacts on plant and in the industry. Don's he was kind of featured on a Science Channel show called Deadly Engineering, where he was featured and interviewed around this disaster too. So some of the snippets from this will come from that. And if you kind of do enough Googling or can get access, you can also watch that. So on that note, I'll hand you over to Don. As I say, please keep questions in the end in the Q&A, and we'll facilitate those and look to answer those at the end of the session. So I'll shut up for now and let you talk, Don. Thanks a lot, mate.
Okay. Thank you, Andrew and Bernie. Well, welcome everyone. What we're going to talk about is Andrew introduced, is the events of August 17th, 2009, which was the catastrophic failure of Unit 2 at a level of failure that I don't think has almost ever been seen in our industry or almost any other industry in terms of the level of unit failure that occurred. 75 workers were killed. 6,500 megawatts went offline. Mostly, some of it went offline for almost 7 years, while the repairs were done. And this plant's powered a good portion of the aluminum industry in Russia, and simultaneously the price of aluminum almost doubled overnight when this plant went down. There's a link here to the show that is a little bit I would call it a dumbed down version, but it has some really nice videos and graphics and other things that I don't have or don't have copyrights to. But so let's get into it. I think there's nothing, picture shows 1,000 words. So we're going to start with a video taken from the visitor center of the failure when it occurred. And to go back to that other picture, you see the dam. This is the powerhouse. This is from a cell phone video, so the quality is not great, but you get the gist of it.
Just a few hundred meters away, filmed just after the explosion, fountains of water can be seen pouring from the base of the facility. What appears to be electrical flashes are silhouetted in the windows. The blast killed 12 people and more than 60 are still missing.
Now, for those of you people who aren't hydropower engineers, this is, this project's almost on the size of 3 gorges. It is massive, and you just lose scale in these videos. I kind of say it's like a scale model effect when you go into a museum and you look at things. This is a massive building that you're going to see some pictures. 100
meters away.
So, at the time, so this failed at 8:13 a.m. in the morning, and Unit 2 catastrophically failed, destroyed 9 units. 1 unit was offline. Unit 6 was in a scheduled outage. The active power of the plant was 4,100 megawatts. When the plant tripped off. You can see some numbers here on the water inflow was 2,350 cubic meters per second through the into the reservoir, and it was releasing through the turbines 2,250 cubic meters per second. So huge amount of flow, but also the head. The upper reservoir was at elevation 537. The downstream was at 325. So 212 meters of head water difference, and the turbines are set lower. So actually it's about 230 meters of head on the pressure containing parts of the turbine that actually failed. So I just want to go to another video. There was a lot of different information, misinformation coming out. And this one has a little graphic about more what failed, and we'll introduce some things we'll go into more detail with.
What are the authorities saying about what actually happened?
Indeed, Alice, for the time being, the main reason viewed by the authorities for this incident is the destruction of turbine caused by the so-called hydraulic impact. It's what appears to have happened is the water, which normally flows from the dam through the generators, surged, and it damaged one of the electrical generators and flooded the vast machine hall which houses all of the electrical equipment. Now, some of the oil was released into the river, into the Yenisei River, but the plant itself was badly damaged, and part of the roof was blown off. Now the generator hall itself looks like the aftermath of a battlefield.
So upon the failure, when the water's shooting out of the top, all units went offline in 49 seconds. So between 8:13 and 8:14, all the units tripped off. All the water flying through basically shorted out all the electrical equipment, flooded the whole lower elevations. Because of how quick it all happened, they were actually unable to close off flow to most of the turbines when the electrical systems were all shorted out in the transformers and substations. I'll come back to a picture here in a minute, but you'll see the transformers were just upstream of the powerhouse against the dam. All the power supply, including backup for all the auxiliaries, was lost for the entire facilities, and their intake gates were not capable of emergency closure to close them off. So the heroes of the day were, one of the operators kept his head together and grabbed two of them janitorial staff. They climbed 240 meters of stairs in the dark up to the intake, and an hour and 7 minutes after the event, they were finally able to get the water shut off to unit 2 so that it kept spouting out of the unit. It took them another 40 minutes to get all the other 9 units shut down. That's actually was only part of the problem, because then they turned off all the turbine water flowing through the turbines, but then the reservoir was fairly full and the water level began to climb in the reservoir, and they didn't have any power to the spillway gates. So they had to get an emergency diesel generator, which took them about another hour to get emergency backup power there so they could begin to open the spillway gates to begin to release water. And so at 11:40, they finally, 3 hours and 30 minutes after the event, were finally able to get the water situation at the dam stabilized and shut off. Here's some pictures of the failure. This is showing the whole of unit 2. Let's see if I can show my pointer options. Andrew, are you seeing a laser pointer on the screen?
Yeah, that's working,
Okay.
mate. Yeah.
So this is unit 2, and sort of a shot down the powerhouse gallery. So I guess I want to say here that these are my opinions of things that happened, of lessons learned. There is some official reports. A lot of people went to jail within Russia, including the plant manager and assistant plant manager who ran and didn't stay to get things stabilized, as well as some of the other people. But there is some information in the public domain, and much has come from some other presentations we have from the Russians, and given it the Russian cold presentations. So some plant information. So here's a nice cross section through the plant here, and you can see here's the transformers and the power transmission lines coming off. And as that water came off, basically all these transformers and electrical lines all got shorted out. These units are, the nominal plant capacity 6,500 megawatts. The plant is in Siberia. It's the 6th largest hydropower plant in the world. The dam is 233 meters tall. It has a crest length of 1,000 meters. And you can see just some of it was originally built in 1971. So at the time of the failure, it was a little over 40 years old, or a little under 40 years old. So here's a shot down the generator hall before the failure. A couple of things to note is these windows and the different turbine units. You'll see here, this is unit 2, the one that failed. So they're numbered 1, 2, 3, 4, 5. You'll see here the powerhouse crane, which is the main way of servicing these, as well as some other cubicle tanks. Right, some information on the project is, for the turbine, actually the maximum power out of that turbine, 735 megawatts. Rated is 650. At minimum water levels, it can still produce 550. The turbine runner itself, which is just the wheel of the turbine runner, is 156 tons. The generator on the other side weighs 900 tons on the rotating parts. And the stationary part of the generator is 500 tons. So a lot of the mass is here. This is very relevant because of the design. The speed on the machine is a 50 hertz power system, and the speed on the machine is 142 RPMs when it's synchronized. Right, so this is a cross section through the turbine that failed. Here you see the runner that I said weighed 160 tons. Here you see the person. So these always help in the picture. The shaft is actually hollow on the inside. So there's a set of stairs inside the shaft. The 730 megawatts of torque is obviously a big enough shaft that they rolled it out of plate or forged it out of a ring, which some of the larger machines like Three Gorges are this way. You can see the person standing on the head cover. This is the pressure containing part and the head cover here. What is really different about this machine is the thrust bearing is up here under the generator, which is fairly normal. But what's abnormal is it has a big cone here that carries the weight of the generator and the rotating parts and puts it on the head cover. So it uses the weight of the machine itself to counteract the hydraulic pressure underneath. And we'll come back to that. This is the generator, but it's good to get a feel for this because I'm going to show you some different pictures. Now I say pay special attention to the bearing configuration because this matters. We're not going to come back to this drawing that often. So up at the top, there is a guide bearing on the shaft at the top of the machine, just above the generator. And it's on a big bracket and it sits though on the stationary stator. We're going to come back, we'll see some pictures of this. Now, the only way it's connected to the structure is through the foundation of the stationary part of the generator. And then there's a couple of struts right up here that give it a support to the wall on the left. Then this lower thrust bearing isn't connected to the concrete at all up here. It goes down to the head cover, and which is bolted to a series of bolts around here called the stay ring flange, which is the stationary ring that these bolt to. And all of this goes here. There is another guide bearing down here at the turbine. So there's a generator guide bearing, a turbine guide bearing, and then a thrust bearing that's kind of suspended up on the air on this big triangular piece. Now, the next picture, this is a picture of that thrust bearing bracket was suspended from the crane when it was being installed. So this is actually the head cover here. And then this is some of the guide bearing and different components going in. So this is a picture you're going to see again after the explosion. Now, some facts about what was going on at the plant when it failed. Unit 2 had been refurbished earlier in the year in April. And after it was refurbished, about in June, it's actually May, about a month later, it started to show an increasing rate of vibration in the machine. And you see here that this solid line here is the limit of where they should have stopped, where they tripped an alarm. So it's about a little under 200 is the peak to peak amplitude vibration in micrometers. And in here you see this is the average, and this is the peak vibration measured by the devices as it went into August. As you see, as they got into August, This was really climbing fast. In fact, many of the 75 people that died was an engineering team that was there to investigate the failure and the increasing vibration and to see what was going on. Okay, but the units was still running. Now, this shows what was going on just as seconds prior to the accident. And you can see a couple of interesting things here. First, I circled the amplitude of the vibration. Unit 2 is at 840. The next closest is at 200. Some of these are down at 50, and those were really low power. And this, so there was a lot of signs that things were going wrong. Another interesting thing going on that no one has been able to explain yet is that the megawatts were at 475, but yet the wicket gates, which control how much water go into the turbine, were 69% open, but it was at 475 megawatts. Look at unit 1, it was 70% open, but at 570 megawatts. And the same thing on unit 5, and even unit 4 at 71, 575. So you can kind of see something else was going on as well. And some of that's not fully explained. Now, a couple of things. And as most critical accidents that occur, they don't happen because of just one thing. They happen because of multiple mistakes when you get to this level of catastrophic failure. First thing that happened was a control room. They had a fire in the control room at a nearby plant. And so the other plant was primarily doing the automatic generation control, which is basically responding to the frequency and holding the frequency at 50 hertz. And they basically put the machine in auto and watch what's going on in the transmission grid. And if the frequency deviates at all, it starts to raise and lower the power automatically. So for some reason, when they shifted the AGC to Sayano, they picked unit 2 for the first responding unit in AGC. With the vibration going on, to be honest, it should have been the last responding unit. They should have never picked unit 2. They should have picked a different unit, but they figured, since the operators didn't know any better, they figured that since the unit had just been refurbished, it was in the best shape. And they had turned off the vibration alarms because they were continually going off. Okay. And then here's what you see. And this is starting at midnight. So what you see is they were at 600 megawatts. They dropped down. And they dropped down and they basically ran in AGC mode between 250 megawatts down to 50 megawatts all night long and ran down in this lower operating regime. And for this type of turbine, we don't normally run here. It can be done, but this is not normal. We can usually find a smooth place or two down here to run, but not to go all over this full range like they did. And then I'll show you again, then they ramped up in the morning, ran up to 600, dropped back through, came back up, and then came back down in the failure. And you can see when they came back up at certain times that the blue is the vibration on the bearing, and the green is the generator bearing. The blue is the turbine bearing. And you can see the different vibration levels that began to climb on them. But yet they kept running. They didn't trip the machine and switch to a different one. Now, this is a very unusual operating regime for any hydropower turbine. And there's why. The blue here represents the efficiency curve of a typical Francis turbine, okay? And there's a rough zone in the middle that happens, and it usually happens between about 40 and 60% power. And this is the blue zone. This is what we call the part load rough zone. And this is not a little bit rough, it feels like an earthquake. It literally, if you're down in the powerhouse, and so every time they ramp up through that, which for this case would have been about 300 megawatts to about 500 or 450 megawatts, they would go through this rough zone. And you see here a picture what's happening underneath that turbine in that rough zone. This is called a von Karman vortex, and it is essentially making all 1,800 tons of rotating equipment bounce upward and inducing a vibration. So what we do when we go up, every machine does this, we just go through as fast as we can, but we try not to go through it too often. And they went through it in a 1 hour period 4 times, twice up, twice down. And then they were sitting down here at the low power at below 250 megawatts, which isn't as bad of a vibration regime, but it is a very tough place to operate because of the angles of the flow that happen. And we get we get little vortexes forming between every blade and the runner as it goes by. So it's a pretty rough regime. And as an old engineer told me, and I found it to be an ultimate truth, right? Any inefficiency that you're running goes into destroying your machine and beating the heck out of your machine. And if they were running down here at 200 and 200 megawatts, the efficiencies were down at 60 to 50%, which means if they're running at 200 megawatts and they're running at 50%, that means 100 megawatts is going into destructive inefficiency, right? And so they were running there all night long, continuously. So let's go through and look at some of the pictures. Here's unit 1. What you see here is a lot of the different parts of unit 2 sitting on top of it. But unit 1, not terribly damaged. Here's unit 2. Here's that cone that we saw hanging from the crane here. This is the generator, the arms of the generators that have been ripped right off. And you see that they're all twisted in a direction of motion. This is actually the rotor rim of the generator here. The stator is gone of the generator, which weighs 500 tons of steel and copper, and it doesn't even exist. All you can sort of see here is some foundation pedestals of where it used to sit. Here's unit 3, cover ripped off, parts of unit 2 landing on it, parts of the crane. Unit 4, again, not too bad. Unit 5, unit 6 was the one that was shut down and was not running. And they were actually able to get this machine back up and running in about 3 months after the failure because it had been out of service for maintenance. Unit 7. Now this is a part of the interesting story besides unit 2. Remember we talked about the bearings in that upper bracket? Well, here the stator is completely gone on the generator. And this bracket was sitting on top of the stator, right? I said that upper guide bearing bracket is sitting on the stationary part. Here's some of the remnants of the stator here, ripped off, and you see the arms, and you also see the torsional pattern that it came off in. The other interesting thing is that all the copper is gone off the rotor poles. There is no copper left on these sitting here. Unit 8 looks decent. Unit 9, here the stub shaft completely is gone. The upper bearing bracket completely shifted off. And again, the stator is completely gone and the copper is gone on the rotor poles. Unit 10, right? Some other pictures, just to give you a feel. Here's sort of the transformer area and that area between the powerhouse and the dam where, you know, probably a lot of the shorting out occurred when the water started to shoot through the roof. Parts of the tail race deck, the unit. Okay, now let's look at some other damage. So this is that head cover piece, and there's a series of things that come into the that control the water into the turbine called wicket gates. What you see here is the stems of the wicket gate shafts completely sheared off inside that upper head cover piece. And you might not know what that is, but if I pull back a little bit, you'll see here, you see all the wicket gate stems completely sheared off here. So it pretty clear it failed in a torsional failure on the wicket gates. And those are probably about, 25 or 30 centimeters in diameter. They're not as small as they look here. And here, by the way, is the head cover flange that failed. Okay, you can see that up here. This was bolted down, and where that thrust cone connects on to the concrete is this flange right here. The flange is not damaged, right? So here's some other pictures of that same area from the other side, right? Here's some pictures. Here's a damaged wicket gate and that sheared off steel. So you get a better feel here how big that was, those sheared off pins were. Here's the wicket gate just torn in half. And this is the bottom half of the wicket gate. The top half are still in the head cover here. And here you can see a collection of bolts that really were the main cause of the failure. And so here's that flange that's embedded in the concrete. And if you look here, you see all these sheared bolts still in the hole. And you can see these bolts have failed here. Now in the investigation claw, and here is some interesting ones. There were, interestingly enough, 6 studs that didn't fail and weren't even damaged, which shouldn't even be possible. Here's the stator core and windings of this is unit 7. All right, so let's go back to here. So these are those wicket gate pieces in yellow here that you see. And these control the flow in and out of the turbine. And here is the head cover flange. The flange bolts are right here that hold this down. So this head cover, from about this point where my cursor is, where it says F1 over to the left edge, that is subject to the high pressure from the upper reservoir at 230 meters of water pressure from here to here. From inside this seal here, the area underneath here is actually connected to the draft tube in the lower reservoir level. So this is a low pressure. And so what they use is the weight of the rotor and the generators to counteract this uplift thrust on it. And so you see the cone here, the thrust cone, and there's another 600 tons of down pull that occurs when we're producing the turbine. So it wants to go down, it doesn't want to go up. There's enough dead weight plus the down thrust to counteract most of the uplift that would occur on the head cover. Right? Some interesting data is that that turbine is 6.2 meters in diameter. It can produce a thrust of 6,500 tons on that head cover if it wasn't counteracted and the seals weren't working right. With the wicket gates closed, it still has 1,600 tons on it. And then that bolt circle is 8.4 meters in diameter. The 900-ton rotor weighs is the same as 4 large locomotives. So to shoot that thing up in the air and to see the pieces you're looking at, you've really got to put them into scale. And then the other dead weight's about another 900 tons for the different pieces. So it's about 1,800 tons of dead weight. Now, here's the other thing. And this is why I was showing unit 7 and unit 9. This unit spins at 142.8 RPM, which the common reaction you get in the power world is that's slow compared to a 2-pole or a 4-pole turbo machine, which spins at 1,600, 1,800 RPMs, right? 142 RPM. However, our diameters are so big that this gives a speed of the rotor pole of 93 meters per second at rated speed, which is 209 or 350 kilometers per hour in terms of speed that's moving. The tips on the rotor is moving at rated speed. Now, what happens when it goes to overspeed and we have a load rejection? This type of turbine, different turbines respond differently. What can go up, the speed can increase by 50%. Once it began disconnected from the load, but it still had water going through it, all those other turbines, they were going to go upwards to about a little over 200 RPM, which would give you a speed of 525 kilometers per hour on the tip velocities on the rotor. So while the RPM is now fast, the end effect, because of how big the radius is on these things, does give you tremendous velocity and power. All right. So fundamental root cause was this unit had a lot of unusual vibration. They ran it in a rough zone and did things they shouldn't have been doing with this machine. Of the 80 head cover bolts, 41 had fatigue fractures. And 6 of them had no nuts on them at all. 6 of them weren't even bolted down. They don't know why. They theorized that the people doing the engineering investigation were going to be mounting something on them, maybe some type of instrumentation on them, on those 6 the next day, but none of those people lived to tell exactly what they were seeing. But there is no doubt that the failure was fundamentally a fatigue failure of these stationary bolts. But there's still a question of what was the triggering event. They really still shouldn't have failed. We've looked at these before with fatigue failure bolts, and they still have a lot of strength left. They don't normally have a catastrophic failure like this, particularly over 80 bolts in a circle. And to fail in shear and not necessarily in tension is very strange considering different things. So here's just a fatigue picture. There's a lot of different things that you can see. We have data on all the different torques on all the bolts and which bolts failed all the way around and what occurred. So there's a lot of different data out there in metallurgy. And some of the bolts were found to have had 90% of their cross section weakened by fatigue. So triggering event is an interesting discussion. Now, one of the things that happens when you trip a turbine off, if you don't have a catastrophic failure, is we close the wicket gates typically in about 10 or 15 seconds to close off the flow. The water tries to separate underneath the turbine as it's going out the draft tube. And then at some point you pull a vacuum and it begins to slam back up and in theory could lift the turbine back up, but it's very rare. And the timing on the wicket gates allow that isn't happen. But a lot of current conclusions suspect that's what happened. And that some event like that occurred, and we had a reverse water hammer from the draft tube. They also looked at terrorist attack or any of the common things, and all those were ruled out pretty quickly. The other event that could cause it is a short circuit event in the generator or the transformer or stator. There is a large torque that occurs when you have a generator short circuit. The third one is a combined event that could have happened in the generator, because for those people who've ever worked in a big generator or big motor, once you synchronize, this motor acts like a giant electromagnetic bearing, and it tries to center the stator and rotor inside the machine of the electrical center of the stator. And so the machine can move a little bit from mechanical center to electrical center. And if it had tripped off for any reason, and all of a sudden the grid and load went away quickly, the air gap all of a sudden became unstable and the machine wants to go to mechanical center. And it can add a large load, and it can actually pull the rotor into the stator and have a small, let's call it a kiss rub between the rotor and the stator of the generator. Now, because of the bearing configuration, one of the theories is that led to that. So we had done a model, and this is kind of that mechanical one, which shows it lifting straight up and sort of coming off. And then the electrical one, you'll see that the generator has a wobble at the top. And in the electrical one, which I more believe, there's many more things that could cause this thing to trip and lose the electromagnetic bearing. And if those bearing bolts were loose, you get a prying action over the 10 meters of height between that rotor and the stator, and can actually pop that off and give it a large shear force between the rotor and stator. And as we showed, those arms were all torn off. I'm going to show this one again if I can get that to do that. Apparently I can't. Let me go back one. So here you'll see sort of the prying action, and picture the lever arm that you get from that type of contact up above it. Well, so one of the things that one of the more interesting lessons learned in this failure was the unintended problems that it created. Like I said, they didn't even have power to the spillway gates and couldn't open it. So now you have a power plant that went offline for, pretty much for 7 years, or most of the plant. They had to release the water coming down through the dam, and they're in Siberia. So you can see here the pictures of the ice that developed on the dam. And they were fighting a constant battle all winter to stop the freezing and the activity on the spillway. This is kind of a picture of the dam. And this is the spillway chutes over here on the left. You can see here they also had a crane over here for the different for shutting things off. There's also power transmission lines, the 500 kV aerial crossing that came across here behind the dam, and a lot of different issues that they had to deal with in the left bank pier. And so you can sort of see the dam came through the event pretty well, and no real structural damage between the turbine and the powerhouse failure and explosion in the dam. And one of the things I've told people is, dams don't have a design life, turbines do. And turbine design life is typically about 30 to 40 years. And these units were coming up on their 40 years. And we're hitting the end of their life, and then they put them into one of the most violent modes of operation you can put them into, and really, triggered the event by the way they ran the machine and by not turning it off. This is some of the issues we had with this different spillway. trying to minimize the icing and keep them open. They had to heat the air intakes. One of the things a lot of people don't realize is air is still a crucial thing to any water flow. And so getting the air intakes kept freezing. They had a lot of grouting that they had to do. They had a lot of damage from the icing and the anti-icing agents that they had to use to keep it down, and all the blasting. They actually damaged the concrete. And then I had to do it every day. So kind of a risky operation. And here, let's see, sort of a similar one. Oh, there's some really good pictures on the different ice formations under different temperatures. Yeah, you're gonna pay me that I want to see the safety on that one for these guys getting up there trying to de-ice these things. Not a job I want. So let's go from kind of the lessons to the lessons learned, which is the point of the exercise. Well, a lot like your car, right? You got to listen and feel the turbines and the generators. Well, we have an older guy, and he literally will go in the control room, and if he feels the powerhouse vibrating differently or all of a sudden a different noise, he will call the control room and go, "What just changed?" Right? And when something changes in a way that it hasn't been doing and doesn't match the units next to it, a red flag should have been going off. And a general rule of thumb is when vibration or noise doubles, you shut it down unless you know why. An increasing noise or vibration, okay, those things happen. But when you see a doubling of it, it's pretty much an automatic trigger that something has changed in a significant way. One of the other lessons learned here is that stationary parts are subject to fatigue. Before this, a lot of the fatigue design being used in hydropower turbines ignored sort of the stationary bolts and anchor bolts. No one was checking them. After this event, kind of a worldwide call went out to check your head cover bolts. And there were projects all over the world that found major fatigue cracks in their stationary bolts. One of the other things that also came to light is that these larger bolts do have a tendency, because their number of threads per millimeter in the old days weren't that much, and it doesn't take much of a rotation to really lose their bolt stretch. And so that these larger bolts are subject to loosening more easy than people think when they check them. Another lesson is that you need to think about, people tend to stop at the coupling. And I like to tell people it's not a turbine or a generator, it's a unit. And yeah, it's got a part that's a turbine and generator, but it's really one machine. And you have to understand how it works and the bearings. This type of thrust bearing configuration where they had it sitting on the turbine is not very common. And I really don't think the plant fully understood all the loads from the vibration that were going to those bolts. The other thing is to know your unit operating limits. And when you change when they went to this AGC mode, there's a consequence. And one, you got to make sure that your equipment was really designed for this. This particular plant had some limited ability to do this, but it was limited to so many hours per year. And they basically violated that in a few days on this one unit as to what it's supposed to do in a year, in terms of the number of hours in that rough zone and the number of ramp ups and ramp downs. The OEMs and the designers of the equipment are the ones that can tell you what this is, what their limits are, and you need to consult them and get their guidance if you're going to change the way you operate. And the other simple one, I mean, if you were going to go on a long trek and you were going to, climb a mountain, you're not going to take your worst car. You're going to take your best car that's in the best shape. These guys picked the worst unit. And that is still almost, to me, the hardest part of this all to explain as to why they picked Unit 2. The other thing that became clear is that the control and protection system, once they lost power, couldn't do anything about it. And so they really hadn't considered extreme events in the design of the system and the protection. Not only did the turbines themselves couldn't even shut off, right? They couldn't close the emergency devices off. So they couldn't even handle the the normal shutdown sequences, they lost normal controls, not to mention not being able to close the intake gates. So the other thing that's come out of this, and this has kind of been known in some places, but not fully appreciated in other countries, is that the intake gates have to be capable of closing against flow. To me, and in the United States and in by ICOLD standards, the device that can close against full flow is the point where the dam stops and the powerhouse starts, right? And they needed to be tested and inspected. Since this time, it took them over an hour and 10 minutes to get that first one closed, an hour and 50 minutes to get all 10 closed. Roos Hydro has now implemented a 2-minute closure time across their entire system for intake gates. They need to be able to push a button and have those intake gates go closed in 2 minutes. For those of us designing hydropower systems and plants, this is something that these gates can be fairly expensive, and the people tend to try to go a little bit cheaper and are always trying to save money. And there's a serious risk of doing those types of things and not having dedicated gates for every turbine. And then the backup power systems need to be above flood levels, and they should be provided up on top of the dam for the intake and spillway. That spillway designs need you need to take into account that the entire plant can go down for long durations. And there's designs considerations that need to be considered for putting the spillway in full-time operational use 24/7 for years on end. And then one of the things that they've done at Sayano is they are adding a massive overflow spillway at the top of the dam that doesn't require gates in order to get the flow down and around. So they've added a second spillway. One of the other things is minimizing the number of people at the lower elevations. There was 75 people at the lower elevations. That's a lot more people than needed to be down at that level when no units were really torn down or were in major outage. There was unit 6, but there wasn't doing much work on it that day. And then operators must be trained in an emergency. I mentioned that some of the plant managers were put into jail. There's video of some of them running out and jumping in their cars, getting out of the parking lot and manually opening the security gates and running for the high ground when this occurred. And this one operator who kept his head together, grabbed some help from, I said, janitorial staff, not operators, and climbed those stairs and shut the gates, may have saved this whole dam and the whole town the whole city downstream of the project. So that's pretty much the presentation. I have some other slides for, such as like the emergency spillway that they're building here and some other things, but I think we want to go to questions for the most part, Andrew.
Yeah, thanks, Don. I don't know if others got the same feeling, but I was a great fan of the Chernobyl TV show that was on HBO a couple of years ago, and I just got kind of memories of that when you were talking through a number of these things with, running plants down low and issues associated with that. So yeah, obviously it doesn't just happen on nuclear power stations, but many others too. So yeah. So we got a couple of questions here, Don. So we'll just run through them, and if anyone else has got any, please throw them in the chat box, and we'll try our best to answer those. So this is from Dalvin. Was there a working high pressure jacking system on the thrust bearing for unit start-stop prior to the event?
Yeah, units of this size almost have to have a high pressure lift system. Just to do, spinning and rotation for just normal maintenance. So I do not know for a fact that they do, but I would assume that they do, that they would have had to have had a high pressure lift.
Okay, and this is from Anonymous. What is AGC mode?
Okay, AGC mode is what is called Automation Generator Control Mode. And it is a mode of frequency control. That you put the unit in, so it automatically ramps the megawatts up and down. So the electrical power grid has to be in perfect balance, supply and demand. If supply and demand are not, you have about 1 to 2 seconds to make corrections to get them back in balance. The frequency will begin to deviate. And at about half a hertz, the breakers of the system will begin tripping. So at about 50.5 hertz and 49.5 hertz, the rest of the system will begin to disconnect the grid from the rest to protect itself. So what you do to deal with the varying loads, you put a machine, and typically it's a hydro machine because they're the best machines for ramping and doing this type of thing. You put it in AGC mode and it follows the load and tries to maintain, in this case, 50 hertz on the node. So if the frequency begins to go up or down, it adjusts the power output either up or down to match. So that is what AGC mode is, and it's happening automatically with no operator decisions. It's simply watching the frequency.
Okay. The next one's from Joe Grilly. Good to see you, Joe. Why was the penstock head gate? Why did the penstock head gate not automatically trip? I think is
they lost power. They lost power to the head gate, and it wasn't set up to automatically trip in the event of a failure. They did have a push button closure from the control room, but they lost power. So they were not able to implement it from down in the control room because they didn't have any power in the control room. The control room completely went down. The battery room completely flooded. So they lost all supervisory control and all power, both. So, and once they didn't have power, then even the normal way you have to lower those gates. They were have dedicated hydraulic cylinders, each one. So they basically had to go to the HPU and manually let the oil out and let the gate begin to drop under its weight by manually controlling the HPU up top of the intake.
Okay, so the next one's around the 2-minute closure time on the intake gates. Was this based on all the intake gates can handle when closing under full flow, or was a full redesign required for the gates?
I do not know, but the 2 minutes is too fast in my opinion. That is really fast for gates of this size and this type of flow and head. We normally tell the turbine designers that they're supposed to design for up to 30 minutes of these types of high-speed events. But a normal closure for us is about a meter per minute, not a meter per, And so at 10 meter, you'd be looking at 10 minutes to close an intake gate like this. We might close it a little bit faster and do more, but these are massive amounts of force, and you got to be careful on how fast you stop it. So 2 minutes is fairly fast for this big of a gate. But we don't know their justification for 2, but it does need to link with the turbine design, and the turbine has to be able to take that overspeed for a certain amount of time, and you have to be within that time.
Okay, thanks for that. That's probably more of a statement than a question, but it's probably holds true to a number of failures. So many failure investigations show the operating team silencing alarms as part of the cause. Operators deal with nuisance alarms on a daily basis, which creates a habit of silencing these, which one can imagine can be very annoying. These false alarms should be minimized to prevent this. You gonna have opinions on that, I suppose?
Oh, this is a tough one. This is where I go, this was more than just turning off the alarm. I've been in powerhouses in a unit that's vibrating like this, and you can feel it in the parking lot. This is not like, and if you watch the TV show that's up on the link, which I think is the other question, somebody asked me to pull this last slide up to see the link, is you will hear the Russians talking about that. You could feel it in the parking lot every time it started and stopped, every time it went up the rough zone. You could feel this unit. So turning off the alarms, I guess, is a normal thing, but it doesn't, they should have shut this unit down. They should not have been running it at these types of vibration. And probably months before that, they probably should have put it in only very limited operation and really probably run it at best efficiency point where there's almost no destructive power and it's well balanced and no vibration. Because there are points that you can run these machines and they don't really vibrate at all.
So it's probably answer 2 questions here. So what destroyed units 7 and 9? Was it just from the runaway or a delay in closing the water flow?
We believe it was a short circuit event. We believe that they saw a major short circuit event in the generator and it torqued right off. You can see in some of the videos, if I were to go back to this first video again, you'll see the flashes of the unit 7 and 9 actually letting go in the video. Let me see if I can play that again. And the short circuit torque is immense. Let's see if I can get this too. If I can get this to play.
Just a few hundred meters
Watch the
away,
flashes to the
filmed
left.
just after the explosion, fountains of water can be seen pouring from the base of the facility. What appears to be electrical flashes is silhouetted in the windows. The blast killed 12 people and more than 60 are still missing.
And the first report actually showed that it was a transformer failure that started this, which is possible. If it started in the generator, they had a transformer failure or some type of major trip out. Like we said, that combined theory would explain what could have happened and could have popped the top off. But there's no doubt the bolts were already weakened and were ready to fail.
Okay, so from Christy, are there any safeguards that need to be put in place to protect workers and the community from such events as this outside of design considerations? Should it be covered in emergency management plans or something else? Or was this just such an extreme event that, you know, you kind of want to be designing this never happens, I suppose?
Well, I think that you know, I have a safety lesson for our internal team where, you know, I go, you know, unless you belong in these spaces and down at these lower elevations and belong in a power plant like this with 6,500 megawatts, unless you're a competent person, you don't belong at those levels. And 75 people, I think, you know, they probably had maintenance workers, janitorial staff, all different types of people down there that probably didn't need to be down at those lower elevations. Back in the old days, they always made sure the control rooms were up high and that the generators and a lot of things were above water level. And as they got into the 60s and 70s, they kind of stopped that practice for some reason. In this case, I don't know how much was below water levels and above, but this was so extreme, nothing was going to survive. I think that it's both cases in this case.
Okay, thanks. Is probably a good, interesting one. What from Shri? What is the recommended frequency of checking head cover bolts for integrity after this event?
I would say 5-year annuals, and then some spot checks in between. If you have a head cover mounted thrust bearing, probably annual. If you have a head cover, a thrust bearing that's mounted on the head cover, and these bolts are also holding the bearings and taking the vibration, I would do it annual. If you just have regular head cover bolts, once every 5 years, and it's pretty easy to do a UT shot down them. In fact, these were so bad, I bet you hit them with a hammer, and I bet you would have heard the cracks in some of these. Just tapping them with a hammer can be an amazing tool to find cracks sometimes. But a quick UT shot down the bolts will tell you quickly.
So Barry Hill's saying, what happened to the copper? I think you said in your presentation it was all gone. Do we any ideas?
Because of the overspeed event and the short circuit torque, it came off the end of the rotor. It just flew off, and then it ripped the stator right off. The rotating parts of the rotor just ripped the stator and the foundation. The bearings twisted off, and the stator just went. The torque is 30. We did a calculation. I need to end the slideshow here, but I forget how much torque the short circuit torque could be. It's an incredible number. Yeah, 36,000 ton meters. So a 400 ton force on each of the 12 sole plates could have happened in a short circuit event.
A big number.
Yeah, it's a crazy big number. And most people don't realize in the air gap, all those forces still can transfer in that air gap. You don't need physical contact The electromagnetic forces that happen in the air gap are tremendous. And like I said, it's a whole dynamic bearing when it's energized and synchronized.
This is from Lyle. Thanks for an excellent presentation. One of the things that happened was the battery room was flooded, forcing the batteries to the other side of the room, compromising the DC tripping supplies. Did they relocate the battery room in the rebuild?
I do not know. I don't have any information on what they would have done, but I hope so. They make notes that they relocated the things they could, and they definitely put some diesel generators up on top of the dam, and I understand another diesel generator at a higher elevation, sort of, but down by the powerhouse at the lower levels. They're like quadruple backup power now to the facility.
This is from Andy Wilton. It very kind of relates to some of the comments you were making a minute ago. What's the usual gap in meters between the rotors and the stators? Interested in the physics of something weighing 900 tons kissing a stationary object and how much it had to wobble.
The typical air gap is between 19 millimeters and 25 millimeters. If it was a floating rim, it might be a little bit bigger, but not much. 25 millimeters is typically the largest, but it tends to be more 17, 18 millimeters. The bigger the air gap, the less efficient the generator is. So they tend to make it smaller.
Okay. So just for your information, Don, I think Joe is saying most head gates in New Zealand close in 30 to 40 seconds, and the fastest Nathan says is they've got one in 16 seconds. So some pretty fast closing head gates.
Well, that's very fast. I would say though that I've been to some of the plants in New Zealand. They're not near as big as these in terms of the size.
Oh, absolutely, yeah.
The overall size. But yeah, that's pretty fast though, I have to say. But they have to be synced. The point is they have to be synced with the turbine design and the control system, and you've got to know. And a lot of these have longer penstocks. If you have a longer penstock, you actually need to close it a little fast. You got to be really careful of closing it too fast because you can collapse the penstock. Short penstocks like this, you could actually close a little faster.
Okay, we don't have too many more. So a few people said that link doesn't work. So you might need an American VPN if you want to dial in there. But
yeah,
I'm sure
or you might have to go to Amazon or one of the others to go, or it's a different name in the UK. It was also shown in Europe under a slightly different name, but still by the Science Channel.
I'll do some digging, see if I can find a link that works. Also, YouTube's usually a good source of information of these things. So. Nathan's asking, was there an automatic intake gate trip system that just didn't work because of the lack of power, or did they not have one?
It was initiated by a command. They did not have it set to automatically trip and close the intake gates. That's a pretty big decision to close the intake gates. So they had it set for, it required a command from the control room, and it wasn't set as an automatic trip closure. It is set as an automatic trip closure now, but they've set it with 2 or 3 different sensors that it's all 2 or 3 of them have to trip. It's got like a double redundancy on it so that there's not an accidental trip of a head gate.
All right. Well, I think that's 1 minute to 1. So, we had an hour. So I think there's a few questions left there, but I think mainly kind of statements. So look, Don, really appreciate you giving this presentation. I think a lot of people found it hugely interesting. I was actually working for a generator client organization in the UK when this happened, and I certainly remember the scramble to inspect lots of bits after this happened. So yeah, the direct impact on my job at the time, because with a lot of our operators had to go and do a lot of emergency inspections for fatigue on head covers and as such. So
well, one of the other things though that happened is we have some clients, and we're aware of numerous cases where they went and all of a sudden automated their head gates to close that weren't automated, and they completely collapsed their penstocks by mistake. because they closed them too fast, didn't have enough air venting in, and completely, there's 3 penstocks I know of that were completely collapsed because they went and added headgate closure when they really weren't ready for it. And Joe's right. What Joe was saying here is correct. You know, there's ways to do it and do it fast, but you know, you make changes to the design, you better make sure you understand the trailing effects of that. I think that's just common engineering, but it's amazing how many people don't think through the consequences of a small change.
Oh, absolutely, absolutely. So yeah, let's yeah, really thanks for that, Don. I appreciate it. It's probably you know, towards the end of your day in the US there, and yeah, I appreciate you taking the time and sharing, you know, the lessons for that to, you know, the engineers in New Zealand and through the New Zealand Hydropower Group. Obviously, yeah, I see a number of our members on here, so yeah, I'm sure a lot of people found it very enlightening, and yeah, we just want to extend our thanks for taking the time
Well,
to
and I
present.
apologize to the non-hydropower engineers. There's no way to do this wholly without using some terms that maybe some people don't know, but I tried. Hopefully.
No, I think you did a great job. You did a great
And
job.
if people have any questions, they can feel free. Andrew has my email. You can send Andrew the questions and he can send them on to me.
Yeah.
I don't think
Okay.
my email is anywhere here, is it, Andrew?
No. If people can reach out to me, I'll funnel
Sure.
through to you if you want, Don. So look, thanks again, and yeah, look forward to the next lessons to be learned presentation through Engineering New Zealand, and all thank you for taking your time today. Thanks, Don, and yeah, look, if that kind of inspires you to be interested in hydropower or as well, and suggest you kind of reach out, and yeah, look forward to seeing some of you at the conference.
We're hiring.
I think everyone's hiring. It's a very busy industry at the minute, so yeah, it's good. So thanks Don, thanks Bernie for arranging that, and thanks everyone for attending, and yeah, have a good rest of your day, and yeah, go and enjoy a beer, Don. So thanks a lot.